Hello and welcome to this demo on load balancer simulation. Today we will be walking you through the design choices that we made, our core classes and structure, how we handle user input, dynamic server management, and how the simulation generates logs and visualizes data. First, let's clarify what a load balancer is. A load balancer distributes incoming network traffic across multiple servers to prevent overloading any single server, ensuring that the overall system remains responsive and available. In this simulation, we will demonstrate how a load balancer dynamically adjusts the number of servers, the active servers, based on the current traffic. So for the design choices, we choose C++ for its memory efficiency and control, which is critical for simulating high traffic environments. Our main logic is in the main.cpp that that calls all the classes that we have, such as the load balancer class, web server class, and the request structure. And it asks the user to input the number of servers and the duration of the simulation, and then generate a unique simulation ID based on this function that uses a hash function to generate a unique ID. And then there's also this function to print for both the log and also the cout or the terminal. This function here is to create random requests with unique IDs based on the hash as well. So first, the main calls input from the user, and then it initializes the requests. After initializing all the requests, adding the request to the load balancer, it also initialize all the servers and make every single busy with one of the requests from the initial requests. Then after, it goes to the while loop, which here's the simulation loop. Then the simulation loop, every cycle increment the time by 1, and in every cycle we go and check every single server. If any server is available, then we add we log that it's processed a previous request, and we add a new request to it. And when the load balancer queue size is less than the number of servers multiplied by 15, so 15 multiple of the number of servers, then we remove this server, and also we add dynamically the servers by doing the same thing with the opposite. So if the queue size is bigger than 30 multiple of the web servers, then we will add a server. This ensures that we can, it will add 2 servers actually. This ensures that we can dynamically increase the number of servers and decrease the number of servers based on the traffic. So also in the while loop simulation, we also have to generate to randomly generate requests during the simulation itself, and we log every single this log is only for the status file, which is a CSV file. We will check how to plot this later. And then here we increment the time. So for the classes, we have a load balancer class, which manages the queue and the time. So it has a function to increment the time, as you can see here. It has another function to get the system time as it is. We have functions to manage the queue, such as adding a new request, getting a request, and getting the size of the queue, or the size of the requests. And for the queue, we also have another class to wrap the queue, which has is empty function to check if it's empty before popping it, and pop to get the request and remove it from the queue. and then push to add another request to the queue, and size to get the size of the queue. And for the web servers class, we have the web server to check if the web server is available or not. So we have two tabs. We have these two types of structs. The first struct is without an ID. Second struct with an ID. So it gives this web server a unique ID to see if to check if it's processed data or not. So here we can add a request to the specific server. It will save the current time, and it will save the request. And then afterward, we can, in the get request, we can get this request back, and get ID. We will get the ID that we saved, and is request available or is request done. It will check for availability for the specific request based on the current time, the updated current time, and the previous current time, which is the start time of the request plus the duration of the time. So if the duration is less than or equal to this, then it means that it's already done. Okay, so for the request itself is basically just a struct to save the metadata of this request, such as the unique ID that we talked about, and also the source IP, the IPN, the source, where it comes from, this IP, and the destination, where it's going, it is going to, destination IP, and also the time, the process time, and the job type. So those are all in the request struct here. So now how we can use this app, can make another terminal here, and then we can just say make run, and it will run and compile all the files that we have to run the main. And now it will ask us for enter the number of servers, which let's say 10. Then here we'll have 10,000. So now after generating this, it will generate the logs, as you can see here. This logs is it will first print the initial IPs for both the requests and the added servers, and then it will print if any changes happen in the load balancer simulation. So for example, here from cycle 26 till cycle 29, nothing happened, but in 29 we had those two requests that got added. So, and here we added some servers, and let's see where we removed some servers. So remove, you can see that we removed the server with this ID. And if we say, like, for example, this server processed this request, if we search for this request ID, we will get that this was part of the initial requests. So and at the end you can see the queue size, and it will print out at the end the simulation has ended with this number of cycles. So after this, we can also plot the data based on the unique simulation ID based on the Python script. So if you run this Python script here, you can paste the simulation ID, and it will here generate this unique plot for every simulation. Every simulation have a unique plot, and in this plot it shows how the load balancer worked. So in the first couple of cycles, it added some servers to match the queue size, because the queue size was large. So it added some servers, and you can see here that the number of servers increased, and then when the queue size decreased, the number of servers kept decreasing, and then until it stabilized in cycle 2000, and it stayed stable towards the end. And you can see here that this is the stable queue size, or the queue region, basically, in this graph. Um, and yeah, so that's pretty much it for our demo today. We covered our design choices, uh, what's in the main, and also we covered all the classes and structures, and we cover how we handle user input, and how we execute them, and then we covered the status. Basically, we showed how it dynamically changes the number of servers based on the queue size, and we showed the status in the log files. And part of the status also is saving every single cycle in a CSV file. So this CSV file saves all the cycles. It has way more lines than has 10,000 lines, which is way more than the 8,000 that we have in the log files. Log files only if there is any changes that happened. And yeah, that's it for the demo. Thank you for watching.